A first-order differential equation is exact if when we put it in this form, m dx plus n dy equals 0, the partials m sub y is equal to the partial n sub x. And kind of a nice way to remember how these partials work with is whatever this quantity is paired with the dx, you take the partial with respect to that opposite variable y. Whatever is paired up with the dy, you take the partial with respect to that opposite variable x. Now, when we have an exact differential equation, we have a nice method of solution. So in order to solve an exact differential equation, what we do is we find a function f of xy that satisfies the following relationships. We want the partial of f with respect to x to be the m function, and the partial of f with respect to y to be the n function. And just to give you the pattern when we look above, we want to make our differential equation have this form partial f sub x times dx. So now x and x agree, plus the partial of f with respect to y times dy. So the y's agree. Now, in order to find such a function, we need to do some calculus. So to undo that partial derivative with respect to x, we need to anti-differentiate m with respect to x. And in the second equation, we undo that partial with respect to y by anti-differentiating n with respect to y. And note what this does is it gives us two representations of the function f, and once we have those two representations, we pair them together to find f. And the thing to keep in mind and be very careful of, the solution is not just the function f, the solution is f of xy equals a constant. Forgetting to set the function equal to a constant as your solution is probably one of the mistakes that I see most frequently. So let's see how this works in a nice concrete example. To solve the equation given here, note it's in this form we would like to see to test for exactness. We have something dx plus something dy equals 0. And I will go ahead and note that the function paired up with the dx is what we previously called m. The function paired up with the dy is what we had called n. But you do not actually need to kind of give these things names. We just remember how we compute the partials. Take the quantity paired up with the dx and find its partial with respect to y. And take the quantity paired up with the dy and find its partial with respect to that opposite variable x. And these are quick, efficient partials. Well, we have 4 and 4, so no surprise for this current video, but this turns out to be an exact differential equation. Now that we know it's exact, we find this associated function. And recall the form that we want to see this differential equation have. We would like to end up with the partial f sub x dx plus the partial f sub y dy. So find f. So we need the partial of f with respect to x to be 5x plus 4y, and the partial of f with respect to y to be 4x minus 8y cubed. And if you can find such a function that satisfies both of these equations, set it equal to a constant, you have your solution. So let's undo these derivatives. So from the first equation, f can be represented as the integral of 5x plus 4y with respect to x. So anti-differentiating, we would have 5/2 x squared. Remember, with respect to x, y is a constant. So its antiderivative would be 4xy, and it's an indefinite integral, so we have plus an arbitrary constant. We do have to be somewhat careful. This plus c represents all quantities whose derivative with respect to x is going to be 0. So that could be an honest constant, but it also could be a quantity involving only the variable y. So I typically will write this as plus c sub y, indicating it can involve y's. Similarly, we have f is the antiderivative of 4x minus 8y cubed dy. So anti-differentiating with respect to y, we would have 4xy minus 8 over 4, so 2y to the fourth, plus now a constant that could potentially involve x's. And we would now like to match up those representations to find a single function f that will work. In order to do so, we just identify what term or terms is present in both equations. And you write those down just once. And then any leftover term somehow has to be accounted for as these constants with respect to x or the constants with respect to y. So f in this case would be 4xy plus 5 half x squared minus 2y to the fourth. And remember, this is not your solution. But setting this equal to a constant, that is the solution to the differential equation.